Welcome to optimizationct.com. In our fourth course, we discussed the sensitive analysis and parametric linear programming. We gained the skill to analyze the impact of the parameter change on optimal solution in this course. What we cover in this course? In this course, we have three key components: sensitive analysis in first three parts, effect of adding constraint, fourth one, and the effect and the parametric linear programming we discussed in the part 5, 6, and 7. First, we will discuss sensitive analysis, examine how variation in the right-hand side and the objective function coefficient impact on optimal solution. This knowledge will empower you to make informed decisions in the resource allocation scenarios. Next, we will explore the effect of the adding constraint to optimization model. We will learn how the feasible region and optimal solution change when new requirement or constraint added. Lastly, we go into the parametric linear programming, where we systematically modify parameter value and observe their influence on the optimal solution. Especially, we will focus on the change objective function coefficient, which is Cj, and the right-hand side parameter, which is Bi, enabling you to understand the dynamic and trade-off within your optimization model. Join us on the journey to unlock the potential of sensitive analysis and parametric linear programming. After obtaining optimal solution, sensitive analysis comes into play. Its purpose is to determine how sensitive the optimal solution is to a specific change in the original model. As mentioned earlier, the linear program assumes that the model parameters such as ij, cj, and bi have certain and definite value. However, in the reality, these parameters are estimated based on assumption and prediction. These estimates rely on incomplete and sometimes non-existent information. The estimates rely on incomplete and sometimes non-existent information. Therefore, the initial parameters used in the formulating the model are considered as empirical estimates. That's why the sensitive analysis is so important. When it comes to the linear programming model, there are a few changes that we typically focus on. First, modifying the value of the right-hand side. Second, adjusting the coefficient of the objective function. And third, introducing the additional constraint. In general, when you make this change, we mentioned in the earlier slide, we can expect one of the three possible outcomes. Firstly, the optimal answer remains unchanged, mainly that both the basic variable and their value remain completely unaffected. Secondly, the basic variable should remain the same, but their value need to be adjusted accordingly. And finally, the entire basic solution need to be completely changed to achieve the optimal solution. The first scenario demonstrates the necessity of the optimal solution to change in the model, indicate the high level of stability. On the other hand, the third case relieves a greater degree of sensitivity, requiring significant modification to the basic solution in order to achieve the desired outcome. When we analyze the sensitivity of the number on the right-hand side, our goal is to determine how much we can change them while keeping the final table feasible. Feasible remains that none of the right-hand side number become negative. To help explain this case, let's consider the following example in more detail. Let's consider an example where we need to produce two products represented by x1 and x2. To produce this product, we use the four resources A, B, C, and D. The available amount of the resources are A equal to 6, B equal to 8, 1 equal to 1, and D equal to 2. The constraints of the problem are defined based on a limitation of these four resources. Additionally, if the profit per unit of the first product is 3, and the product per unit of second product is 2, the model can be summarized here. So we have 2 decision variable and 4 constraint. The optimal solution of the problem, which is determined by point C, which is here. This is the point C. We have x1, x2, and 4 slack variable. In the optimal solution, we observe that the resource 1 and 2 are fully utilized, while their level of resource C 3 and 4 are 3 and 2 third, respectively. This example show us the following question. So what is the difference between constraint 1, 2, 3, 4? So we'll discuss in this slide. How flexible are resource amounts, number of on right hand side to decrease or increase? Once you have found the best solution, we can explore the potential chain to further optimize it. Especially if we focus on 2 types of analysis. First, how much can we increase the resource to enhance objective function optimal value? Second, how much can we decrease the resource without altering the current optimal solution? As the resource level are represented by number of right-hand side of the constraint, this analysis is known as a sensitive analysis of right-hand side. In the given problem, only constraint 1 and 2, which correspond to a resource A and B, are significant. Common sense tells us that if a constraint is important, it means a limited resource because all valuable resources are fully utilized. It causes S1 and S2 is equal to 0. Conversely, a constraint represents as abundant where F3 is not equal to 0 and S4 is not equal to 0, which call this constraint as the abundant constraint. Therefore, our interest lies in determining how much we can increase scarce resource to enhance objective function value. Similarly, we want to find how much we can reduce non-scarce resource without impacting the optimal solution. Let's see this figure. Constraint 1 and 2 indicate the limited resource. Let's focus on the resource A. As we increase the amount of resource A, constraint A, which is line CD, shift upward in the parallel manner, causing triangular CDK to shrink. Here, the side CK and DK of the triangular DKC correspond to the constraint 2 and 4. As we continue to increase the resource A, we reach point K here, where the constraint 2 and 4 become significant. At this point, the optimal solution is located, and the feasible region is represented as the area A, B, K, E, F. When we further increase the capacity of the first constraint moves upward and maintains the parallel relationship to itself. However, this increase has no impact on the feasible region or improving the objective function beyond that point K. This is because the first constraint becomes redundant and the value of the first constraint will keep increasing till point K. The first constraint will intersect point K if right-hand side number is greater than 6. To calculate this increase, we simply substitute the coordinate of point K into the first constraint. In this way, the maximum increase in the first limit is from 6 to 7, which is equal to 1 unit. Okay, the diagram below illustrates the impact of the increasing of second constraint. Independent of any change of the first constraint is very important. As we increase the second constraint, we can improve the objective functions until the second constraint intersects point J. Here, this is point J. The coordinate of point J are determined by intersecting the second constraint here and the non-negative constraint of the variable x2, which is x1 is equal to 6 and x2 is equal to 0 as shown here. By substituting the coordinate of point J into the second constraint, we can calculate the new value of the right-hand side number in the second constraint and updated value of the resource B. So this is here we can see that the resource B can be B is equal to 12. As a result, we can increase the right-hand side of the second constraint from 8 to 12, which is amount of potential increase of 4 units. Let's now examine the decrease in the right-hand side number of the redundant constraints. Because S3 and S4 are non-zero, the constraint 3 and 4 are considered as a redundant. Let's focus on the constraint 4 first. The diagram below illustrates that the first constraint, line ED, can be reduced till it crosses point 3 without impacting the optimal solution. Point 3 corresponded to x1 is equal to 3.3 and x2 is equal to 1.3. Therefore, the right-hand side number of the first constraint can be decreased to a maximum of 1.3 without altering the optimal solution. Now consider the third constraint. Again, similarly, we can decrease the right-hand side of this constraint such that the equation here, minus x1 plus x2, which is equal to 1, which is third constraint, pass through the point 3. So the right-hand side of the third constraint become here. You just need to point C here in this equation. What is point C? Point C is here. Let me see, is 3.3 and x2 is 1.3. This is the coordinate of point C. So therefore, the right-hand side of the third constraint become minus 2 by doing this calculation. This modification has no impact on the current optimal solution, which is point C. The findings from the preceding discussion for 4 constraints are summarized in the table here. As you can see that we have 2 constraints as a scarce variable, as a scarce constraint, and we have 2 constraints as a redundant constraint. You have the maximum change in the Z value and the maximum change in the right-hand side value in this resource. Considering the financial constraints that are commonly encountered in the economic aspect, we would like to determine the importance of the capital allocation among the different resources. Our main objective is to maximize profits, so we are interested in identifying the resource that can contribute the most profit growth. This information is represented in the table below. So if yi represents the value of each unit of resource I, we can calculate yi using the following formula. So you can see that the resource 1, 2, 3, 4, resource 1 and 2 are the scarce constraint, and resource 3 and 4 are the redundant, and y1 and y2 is positive, and y3 and y4 is 0. We will discuss in the future that y1 and y2 is a shadow price of the first and second constraint. In this part, we are trying to deal with the sensitive analysis of the objective function coefficient. Modifying the coefficient of the objective function impact the slope of the objective function line. If this modification exceeds a certain threshold, it can lead to a change in the optimal point. Consequently, a set of critical constraints and the type of resource, whether they are scarce or redundant, can be affected. The object-insensitive analysis seeks to address the following question: how much coefficient of the objective function can be changed, increased, or decreased without changing the optimal solution? In the previous example, let's denote the coefficient of the objective function as C1 and C2. The objective function can be expressed as follows: z is equal to C1t times x1 plus C2 x2. As depicted in the diagram below, when C1 increase and C2 decrease, the objective function line rotate clockwise around point C. Conversely, as a decrease in C1 or an increase in C2 cause Z to move counterclockwise. Therefore, point C remain optimal until the slope of the objective function Z lie between the slope of the constraint 1 and constraint 2. If the slope of Z align with the slope of first constraint, the problem will have the two optimal corner point, which is C and D here. Similarly, when the slope of Z coincide with the slope of the second constraint, line CB, the 2 points C and B will be optimized. Any slight change beyond the defined range for C1 will result in new optimal solution being located at point B here or D. To calculate the range of change, we first fix the numerical value of the coefficient x2 and denote the coefficient of x1 as C1. This diagram illustrates that we can increase C1 till it reaches the second constraint line CB, or decrease it until it reaches the first constraint, which is CD. As a result, we can determine the minimum or maximum value of C1 by aligning the slope of Z with the slope of the first and second constraint. The slope of Z is equal to minus C1 divided by 2, while the slope of first and second constraint is minus 0.5 and minus 2. Respectively. Thus, we can find the minimum value of C1 using the following relationship, minimum and max. Likewise, the maximum value of C1 to maintain the optimality at point C can be calculated here. So, the range of allowable change for C1 to retain optimality in point C is between 1 and 4. When C1 is equal to 1, the optimal solution will be either point C or D. We have the multiple optimal solution. If the value of C1 decreases below 1, the optimal solution shift to point D. Similarly, it holds for C1 being equal or greater than 4. If C exceeds 4, if C1 exceeds 4, the optimal solution shift to point B. Let's go to the next part, adding a new constraint. Once a problem has been solved and the optimal solution has been determined, there may be possible where a new constraint needs to be added to the existing set of constraints. This new constraint could potentially reduce the feasible region or have no impact on it. This effect can be observed in the following two cases. First case, adding a redundant constraint. As I mentioned before, a redundant constraint is one that has no impact on the feasible region and therefore does not affect the optimal solution. Referring to previous example as depicted in the diagram below, here, if we add the constraint x1 plus 0.5 x2 is less than 5 to the existing 4 constraint, it will not alter the feasible region. So this is the redundant constraint. and the optimal solution will remain unchanged. Adding an effective constraint. So this is the next part in adding a new constraint. An effective constraint refers to constraint that has an impact on the feasible region, potentially leading to change in optimal solution. For instance, considering the constraint here, this constraint narrow down the feasible region, consequently alter the optimal solution from z is equal to 12.66 to z star is equal to 9.5. Now let's go to the great general case, which is parametric linear programming. During the sensitive analysis, we study the discrete impact of the model parameters on the final solution. However, when we need to examine the effect of continuous change in the parameters across the various possible values, we utilize the parametric linear programming. The systematic change of the parameter Cj is the first part. Let's consider the given objective function. Here, this is the objective function. In the parametric programming, we replace the objective function with the following function. Here, aj represents the constant data that determine the rate of change in the objective function coefficient. We increase the value of theta from 0 to demonstrate the effectiveness of the linear programming model as theta varies. Let's examine the following example. Let's consider a1 is equal to 2 and a2 is equal to -1. So the objective function can be written as follows. Starting with the final simplex table with theta is equal to 0, the objective function becomes here. We incorporate the change in the objective function on the left side, resulting here. So we change the objective function by this part. Since x1 and x2 are a basic variable appearing in equation 2 and 3, their coefficient in the objective function should be 0. This can be achieved by adding the equation 2 and 3 to objective function as elementary operation, as we discussed in the earlier course. That's yield to here. Based on the stopping condition of the primal simplex method, if the coefficient of the non-basic variable remain non-negative, here the basic feasible solution is considered optimized. Therefore, in our case, this condition holds true. Okay, if theta hold this condition, here we have the optimal solution with the basic variable x2 and x3. Hence, if theta become greater than 9/7, we select x4 as an incoming basic variable because it has a negative coefficient in the objective function. And a new optimal solution obtained using the prime simplex methods. The new simplex table with the x entering base and x3 leaving the base based on the ratio test is as follows. So if theta become greater than 5, we choose x5 as an incoming basic variable, and a new optimal solution is obtained using the simplex method. The updated simplex table with the x entering as a base and x2 leaving the base determined by the ratio test is as follows. As seen here, this is here, as we increase the theta is greater than 5, we have this table. As seen in this table, when x5 exceeds 5, all 0 rows remain non-negative. So we can see that if theta is greater than 0, the coefficient of the objective function in row 0 is greater than 0. This implies that the value of the theta can be increased indefinitely without affecting the basic variable. The overall result of this procedure for various theta are summarized in this table. So it depends on the value of the theta, you can pick one of these three tables. Also, the value of the objective function as a function of theta is depicted here. So you can see that if theta is equal to 9/7, you have the minimum objective function. Let's go to the systematic change in the right-hand side parameter, which is bi. In this scenario, the parameter bi is substituted with bi plus alpha I theta, where alpha I represent the fixed data. Consequently, the problem can be expressed as follows. The objective function of this section is determine the optimal solution as a function of theta. Altering the coefficient of the objective function in the prime model is equivalent to change the coefficient of the right-hand side in the dual problem. This is a very important point we use here. To provide the further information, we will work through some example here. Let's apply the parametric linear programming approach to systematically change the value of the bi and determine the optimal solution for following problem. Consider the theta value ranging from 0 to 25. Based on the value of the theta, we obtain the optimal solution for a given model as presented in this table. So you can see that this is the optimal solution, optimal table. For the value of theta between 1 and 0, the last table, this table, would be optimal because the right-hand side would be positive if the theta between 0 and 1. However, for theta greater than 0, the variable x4 exit here. The variable x4 exit and x5 enter the base using the dual simplex method. In the optimal table, the optimality remains intact for theta ranging from 1 to 5. Here. Nevertheless, for theta exceeding 5, if the theta between 1 and 5, this is the optimal solution. If the theta exceeds 5, the variable x2 here leave the base and the variable x3 enter the base. In the next optimal solution table, for the theta greater than 5, the optimal condition and feasibility table will remain unchanged. The corresponding simplex table is provided for theta is greater than 5, condition theta is less than 25, as we discussed in the example. So the results are summarized in the table here. So depending on the value of the theta between 1 and 0, 1 and 5, and 5 to 25, you can have the optimal solution for decision variable and the objective function. Join us in exploring more examples and expanding your problem-solving skill. Visit our website to access a wide range of problem-solving scenario and exercise. By solving this problem, you can enhance your understanding of various concepts and techniques for the systematic change in the parameters, which is coefficient of the objective function and right-hand side. Visit our website. Now get started. Thank you so much for watching us. If you are really interested in our website, you can visit our website. Also, if you have any question, you can send by an email by optimizationcity@gmail.com or fill the contact form in our website, which is www.optimizationcity.com. Thank you so much and bye-bye.